Good. So what should be a pretty quick one here today. All we're looking at the second part of section 2.2. We're looking to identify our three-dimensional figures, calculate some surface areas, some volumes, and flatten them out into nets. None of this is new, but we're looking at this through a secondary school lens. So this should be super straightforward if you have our prerequisite skill, which comes from the first half of section 2.2. That's our working down. You must be able to work down if you're able to work through right here. When we are working through this, if you're watching this video and you're not in one of my classes, this is really only going to be super helpful to you if you have access to a formula sheet that gives you your surface area and volume formulas for given three-dimensional figures. If it does not, it can still be really helpful to you, but you'll have to memorize these formulas on your own. So we have ourselves here three figures. We're just going to look at this first one first. All we're doing, we're identifying, hey, what figure do we have with it? And then we're going to identify what formula will be helpful to us. So we're identifying, hey, look, we have this figure right here, and we need to identify, hey, is it a cylinder, a sphere, a cone, a square-based pyramid, a rectangular prism, or a triangular prism? Now, you'll notice these we're working with a cylinder, a rectangular prism, and a triangular prism. All of those have something in common, and that is two opposite sides that are exactly the same shape. So with the cylinder, we have, and really a cylinder could be viewed as a circular prism, right? A cylinder can be built just from taking the same circle and stacking it right on top of each other. You can kind of think of like a Pringles can, right? If you're trying to stack exactly the same shape on top of itself, you'll end up with two of the same shape on the top and on the bottom, and then in between, you'll end up with a straight flat edge connecting the two like this. That's true for a cylinder. That's true for any prism, right? We can head down and take a look at our rectangular prisms, and we could build a rectangular prism in the exact same way. Where we have here, okay, we have a rectangle on the bottom, and then we have on top of that, it's like we have the exact same rectangle getting stacked on top of itself right here. And if you're trying to visualize this, you can think of like a deck of cards, right, where you have one rectangle copied again and again and again, and together it creates one rectangle on top, one rectangle on the bottom, and then straight edges connecting the two rectangles themselves across. A triangular prism, this is true for every single prism. A triangular prism, same thing. We can look at our base triangle across the bottom, and then the same triangle being stacked on top of that again and again and again, which creates this prism shape. So any prism you can recognize because the top and the bottom are really because opposite sides are the same with straight edges connecting them. Now we're identifying over here that, hey, we have ourselves one of these kinds of prisms. What kind is it? Is it a cylinder? Is it a rectangular prism? Is it a triangular prism? We're going to take a look and just identify, hey, what is this side that shows up? What is this side that shows up that's parallel, that's the exact same? And we can see there are actually multiple arguments when we're working with a rectangular prism. The two that stand out to me, I'm working right here at the top, is a rectangle, and this exact same shape, and it's kind of tough to see because some of it's hidden by the rest of it, would be down here where we're working with two rectangles that are identical right there. So because they're rectangles, the kind of a prism we're working with is a rectangular prism right here. Then we're looking to find the equations that we can use to calculate the volume. So let's head back to our formula sheet, and we'll need to be careful. Okay, so we'll head all the way down to rectangular prism. So when we're looking at volume, we're going to look way over here. We're heading over, and we can see that we have two equations we could be working with. We'll have to identify what we want to use. Volume is equal to the area of the base times the height, or the volume equals length times width times height. So it depends, your viewpoint. If you like to view this as breaking it down into the pieces, then area of the base times the height is going to be really helpful. If you like to look at your formula and look at your sketch of your figure and just plug and play your numbers into it, then this bottom version is going to be way more helpful to you. But you will notice when we're working with our prisms, the volume of the prisms are all calculated in the same way. That is, the volume is equal to the area base times the height. Even if we head up to our circular based prism, which is our cylinder up here, the volume is equal to the area of our base times the height. So which one's going to be most helpful to us when we're working with our rectangular prism? I think it's going to be this one. It includes our length, our width, and our height. That's what we would be looking at. Those are the necessary dimensions that we would need. So our volume is equal to length times width times height. Fantastic. I'm working with a prism over here. That's our circular-based prism. That's our cylinder. And I'm working with a prism down here. Whoops, it's cut off a little bit down here. That's a triangular-based prism that we're working with. And we notice, again, each of them will have opposite sides that are identical. In this cylindrical case, we can see that we'd be working with something like this in the bottom and a circle in the top. With the triangle, again, one of the sides is hidden down here. It's hidden at the bottom. Let's see if I can get it to show up a little bit better. Something like this is what I would be looking at, where I can see that my bottom shape is the same as the top shape. So pause the video here and copy out the necessary formulas that would be helpful to you if you were calculating these volumes right here. Good, well, you'll notice right here, for the cylinder, nice and straightforward, I pulled that equation right from my formula sheet. For the triangular prism, I have two options, right? I can choose for the triangular prism, I can choose this option or that option. Either will work. You just need to make sure you're comfortable performing those calculations right there. I chose to show it as a fraction right there, your choice. Next, we have two other shapes. And if we look closely at these two other shapes, we'll notice, hey, these are not prisms. These do not have two parallel sides that are identical to one another. In fact, each of these has one side that's a base, and then from there, all of the sides go into a point. With the cone, it goes into a point at the top right here. With the pyramid, same thing at the top right here. And we notice from the very top point, the side or lateral sides that connect the two could reach the bottom of the base all the way. It goes straight down all the way around. Now, this might look a little bit wonky. That's okay. We're working here. We're gaining a little bit of comfort working with these shapes. When we're calculating the volume of a pyramid instead, let's take a look at our formula sheet. We have a cone, which is kind of like a circular-based pyramid that we're working with right here. And we have a square-based pyramid right here. When we're calculating these volumes, I notice it's really similar to that of a prism, where we had the area of the base times the height, except now we're just dividing it by 3. Area of the base times the height divided by 3. That's going to be true no matter what when you're working with a pyramid. And we will need to choose a more helpful equation. Although these equations that I've highlighted so far can help us understand where the formula comes from, they're not going to be what we're substituting our values in. We'll be substituting our values in to either of the next few pieces. If you prefer to show the whole thing as one fraction, then you're going to be working with these two versions. If you prefer to work with one fraction and then multiply that by a bunch of numbers, we'll work with these two versions. Either way, your choice. You can mix and match if you would like, but you're responsible for understanding how to use these formulas. Good, so there we have our formulas that will be really helpful to us when we're calculating the volumes of these shapes. You are responsible in the future. You will get this formula sheet, and you will need to pull out from that the formulas that you are comfortable working with. Next, we're just going to look at our surface areas. That is, we're going to use the middle column when we're working forward right here. We're going to use the exact same shapes, the exact same figures that we were working with, but this time we'll practice bringing their surface area formula out. So we already know that our first figure over here is a rectangular prism, so we're working with a rectangular prism, and we're recognizing, hey, this only has one formula in here. That's the one we need. Nice and straightforward. Then we're working with a square-based pyramid. And all of a sudden with a square-based pyramid, we see a whole bunch of different pieces to our formulas over here. And we notice, hey, what are we going to be looking for? Well, we'll look for the surface area. And that is, if we're working with this figure, the surface area is going to be the total area that we have. And then they break down exactly where this formula comes from. Well, it's 4 of the areas of the triangles along the side. So that's like one triangle right here, one triangle right here, and then 2 across the back. And then plus the area of the base. And the area of the base is just this little square in the bottom as well. So that's great. That's really helpful that they tell us how they build, there we are, the area of the base. That's really helpful that they tell us how to build their formulas, but we actually don't need that, right? They can tell us where the area of the base comes from, where the area of the triangle comes from. That's all well and great. What our main focus is on is the total area is equal to this. And if we're not sure, hey, what does B represent? What does S represent? Well, that's when we're taking a look at the image or at the sketch on the left side right here, and we're saying, okay, where does our B show up? Oh, our B shows up here, so it must be the length across the side of our square that's on the base of this pyramid. And the S, what's the S? Oh, that looks right here. It looks like it comes from the middle of one of the sides all the way up to the point, so that's that distance right there. If you don't have that distance, you'd have to calculate that, usually by using your Pythagorean theorem from some values that you've already been told. So the formula that we're using right here is going to be 2 times the length of the base times the slant height plus the length of the base squared. Now, every single time you're looking at your surface area formulas, they're going to tell you the same thing. They're going to tell you the areas of the different pieces that are involved. Then they're going to tell you how they combine those pieces to find the total area. And then lastly, they're going to tell you, hey, look, this is the equation you can plug things into in order to calculate the surface area. So every single time they're working in that same way where they're telling you how your equation is built, if it's applicable, and after that they're saying, hey, this is what you can plug your numbers into. So take a moment, copy out the relevant formulas onto your page right there, and then we'll move forward. Good, so this is what our formulas are looking like once we have selected really appropriate formulas to help us forward. Now let's take a look at example 2. So example 2, we need to calculate the volume and the surface area of this figure that we're working with. Now, that's all great because we've already chosen our suitable equations right here. What shape is this? We're working with a cylinder. And if that's the case, I want you to pull both of your relevant equations from the previous page. Good, okay, so we have our relevant equations. Now it's up to us to identify, okay, what do each of these letters represent, right? When we're working with a cylinder, the R is your radius. So your radius is the distance from the outside of the circle to the middle of the circle. Then, so that identifies our R there, our R right here, our R right here. But we also have an H involved, so we need to identify, hey, what's the H? The H is always going to be the distance between the two circles. So in this case, it's 11 meters. Now, sometimes your height, sometimes you can end up with a cylinder that's sitting on its side, and your height will actually be the distance across from circle to circle. So your height always won't be up, down, but it will always be the distance in between your two flat faces. So if our height is 11, our radius is 4, then we can perform our calculations using our working down skills. I want you to pause the video here, try and calculate both the volume and the surface area, and then unpause to see how you did. Good, so we've performed our calculations. You can follow my working down. You can see that my equal signs are fully lined up, and you can see that I've tracked my changes on each line as I make my way through. So I found the volume, I found the surface area. Last piece right here, make sure you consider your units. In this case, we're working with meters. Whenever we're working with volume, we're going to be working with a cubed unit, so that's meters cubed. And if we're working with surface area, we're going to work with square units, so that's meters squared. Lastly, we're working with nets. Net is a three-dimensional figure. It's been unfolded so that it looks really flat. It allows us to clearly see all of the sides, their shapes, and their dimensions. So let's take a look at how many sides that we would have with each of these figures. I encourage you to pause the video, try it out, unpause, see how you did. We're working with our rectangular prism. We remember that we have some hidden sides showing on the back. We can see one side on the top, two sides on the bottom, and then we have 3, 4, and then 5 and 6 are on the back sides around here. Number of sides 5, sides 6, so we have 6 sides right here. With our square-based prism right here, square-based pyramid right here, we know that we have, again, some hidden sides. We have the nice flat side along the bottom underneath that we can't see right here. And we have 4 sides that are slanted around the top. That is sides numbers 2, 3, 4 is around the back here, 5 is around the back on the other side. In total, 5 sides. And lastly, with our cylinder, we have one flat circle across the top, we have another circle on the bottom, and then we have our third side is a rounded side. It does not need to be flat, but it goes all the way, it reaches all the way around this cylinder right here. In total, that's 3 sides. So if we have 6 sides, 5 sides, 3 sides, whatever number of sides we have, that's how many shapes need to make up the net that we're working with. So in this case, right here, when we are working with a rectangular prism, then we can see, okay, we have sides 1 and 2 are identical but opposites. Sides 3 and 5 are identical but opposites. Sides 6 and 4 are identical but opposites. So we're working with sides 1 and 2. We could work with, say, like this, where we know that they're not touching each other, so I have to leave some space between them, but there is just one side right here that goes in between them, so I can draw that, say, as side 3. And then side 3 has an edge with side 4 and with side 6. And if I wrapped up sides 4 and 6 upwards, if I wrapped up sides 1 and 2 upwards, I could start to build a box. In this case, the box wouldn't have a top. I need to get a top on that box. That's our last side right here. That is not touching side 3, but it is touching side 6 right here. Now, there are many different orientations that we could build right here, but all of them need to make sure that, that the opposite sides are not touching. That is, 2 is not touching side 1. Side 4 is not touching side 6, and that is, lastly, side 3 is not touching side 5. Good, so really we're seeing, hey, where are some edges that can connect our sides? We can see some edges around right here if I'm working with my square-based pyramid. If the base is a square, that's side 1. I have a triangle coming out from each side of the base like this. They should all be identical triangles. You can tell from my sketch that they are, wow, fantastically, exactly 100% identical. Great job, Mr. Pasotka. Lastly, our cylinder, we have 3 sides. Sides 1 and 2 are not touching, so they have to be far apart. And if we unrolled our cylinder, we would actually find that side 3, it's not rounded at all, it's just a rectangle. Right, side 3 right here, and side 2. I will narrate at the very least that sides 1 and 2 are perfectly drawn circles, and they are opposite one another. They are equal to one another. When you are sketching your nets, we don't need to number our sides, all right? That's helpful for us as we're going through this practice, that we can see, hey, how many sides do we have? Hey, which sides are where? But when you are coming up with your net, we don't need those at all. We could just draw our nets perfectly like this. All right, so nice work. I'm hoping you're feeling a little bit more comfortable working with your nets, calculating volume, calculating surface area. You should be ready for the practice here.